Hello everyone, thank you for watching this video. My name is Junah Hong from UNIST. I'm excited to present our work, CMASan, Custom Memory Allocator-aware Addressing Integer. This work was advised by Professor Yuseok Chun and conducted in collaboration with Rensselaer Polytech Institute and University of Maryland. Addressing integer is the most widely used practical approach for memory bug detection. ASAN surrounds each object with resonance to catch buffer overflows, and poisons freed objects for UTF-free and double-free detection. These freed objects are then placed in the quarantine zone, delaying reuse and extending the detection window. To support this mechanism, ASAN replaces standard allocators such as malloc or free with ASAN's own internal allocators. This allows ASAN to work properly with standard allocators, but here's something to think about. What happens if the target application uses a custom memory allocator that ASAN cannot replace? In that case, ASAN will miss semi-allocated objects, so bugs affecting them go undetected. To understand how often this issue arises in real-world applications, we analyzed 100 projects and found 78 CMAs that cause false negatives in ASAN. Interestingly, they fall into two dominant patterns, arena and recycler. Arena CMAs allocate a large memory region and place objects within the arena. However, because ASAN only replaces standard allocators, there are no redundancies between these CMA objects. As a result, ASAN fails to detect buffer overflows. In the recycler pattern, CMAs repeatedly allocate and free the object without returning it to the standard allocator. Consequently, ASAN fails to detect UTF-free and double-free on the CMA object. So we need to place redundancies between CMA objects and poison and quarantine them before reuse. To address these first negative issues, two solutions have been proposed so far, SHIM and ASAN poisoning APIs. SHIM provides a mode to switch CMAs to standard allocators so that ASAN can replace them. However, not all CMAs are compatible with standard allocators. For example, in-place real where the object is resized at the same memory location, or a clear API that clears all the objects in the arena at once. ASAN poisoning APIs allow us to manually insert poison and unpoisoned calls into CMA logic to update shadow memory. However, redundant space must be manually secured, and it does not naturally support the quarantine zone. Ultimately, both require manual code modifications with a deep understanding of CMAs. To overcome these limitations, we present CMASan built on top of ASAN to detect memory bugs on CMA objects without requiring manual code modification or expert knowledge. First, we start by identifying CMAs from the source code and instrument the CMA APIs. At runtime, we maintain on-demand metadata storage for efficient object tracking and instance-specific quarantine zones for longer detection windows without replacing CMAs. It also avoids false positives that can arise from instrumenting CMAs. Let's begin with CMA identification. For CMA identification, we extend the existing CodeQL heuristic rule to identify CMA alloc candidates and categorize CMA family functions based on user responses. Based on this identification research, CMASan instrument the CMA APIs. For alloc, CMASan extend the size argument before the calls to secure redundant space, poisons the right side of the returned object, and saves the metadata using the beginning address as a key. This metadata is retrieved as free using the parameterized pointer, and checks for double free if the incoming object is already freed. Then we poison the object and update the metadata. Real instrumentation is similar to alloc, but we additionally compare the returned object with the old object to distinguish in-place behavior. Specifically, we poison the old object only when real returns a new one. Furthermore, since clear API frees all the objects at once, we record allocated objects in the corresponding allocation zone and poison them on a clear API call. To manage metadata required for CMA object tracking, efficient metadata storage is necessary. Since CMAs manage their objects within a relatively narrow memory region, CMASan utilizes a two-level table for metadata storage, creating second-level tables on demand. As a result, CMASan can maintain second-level tables only for CMA-managed memory region. To enhance UTF-free and double-free detection, we design a quarantine zone under two objectives, free delaying and instance-specific. First, we need to delay the recycling of objects while preserving CMAs, whereas ASAN simply controls its own allocators. Without delaying, if an object is freed by CMA, it may immediately be recycled and allocated before bug detection. So we introduce a free delaying quarantine zone, which intercepts the object before it is freed by the CMA, poisons it, pushes it into the quarantine zone, and pops the first in object. Then we pass the first in object to the free instead of the currently requested one, enabling a quarantine zone without modifying CMA's internal logic. Additionally, we need to distinguish the quarantine zones between different CMA instances. But why is this necessary? Suppose there's a single quarantine zone shared across all CMAs, then who's free might get the bar-based object, leading to metadata corruption and incorrect behavior. To prevent this, we place each object into its own quarantine zone based on CMA ID stored in metadata. Now we have an instance-specific free delaying quarantine zone, again without modifying CMAs. Since we instrument CMAs without modifying their internal logic, false positives may arise from CMA's legitimate behavior. Let's see how we avoid this. First, CMASan suppresses the approach if a CMA API is in the code stack, because CMAs may legitimately access poisoned memory. Second, we activate instrumentation only for the outermost CMA to avoid incorrect return sizes and double free false positives from nested calls. Finally, CMASan returns the original size of object on size-pairing APIs, since CMAs treat residence as part of the object. For the evaluation, we target the top 12 C++ applications that utilize CMAs from GitHub and compare CMASan with ASAN and COSAN. We evaluated CMASan on 5 metrics. Here, we focus on 3: detection coverage, performance of red, and unknown bug detection. To show how CMASan improves ASAN's detection coverage, we measure the number of CMA objects and how many ASAN checks actually hit them. We can see that CMASan recognizes many CMA objects overloaded by ASAN, and up to 87% of load store checks are on CMA object, which means that ASAN is unaware of these objects, allowing related bugs to go undetected. Also, CMASan incurs only 1.096 times performance overhead and 1.148 times memory overhead compared to ASAN, thanks to our on-demand metadata storage. Lastly, we apply CMASan to real-world applications. CMASan detects 19 previously unknown bugs, including ones undetected for 9 years and 2 years in SQLite3 and PHP, respectively. Moreover, ASAN and COSAN miss all these 19 bugs. As a conclusion, CMASan effectively detects all types of CMA-related memory bugs, identifies 19 previously unknown bugs, incurs 9.63% performance overhead compared to ASAN, and extends ASAN's coverage without replacing CMAs. Thank you for listening. If you're interested, the QR code will take you to our full paper and open source repository. Thank you.